In this lesson, we're going to explore the chemistry of radicals, and in doing so, take our first steps into looking at reaction mechanisms. A radical is simply any molecule or atom that has an unpaired electron. And because it has an unpaired electron, that means that one of the atoms has an incomplete outer shell, or an incomplete octet typically. And that means that radicals are typically very, very unstable. So here I've got a couple of examples. We have a bromine radical, and you can see that it only has 7 electrons in that outer shell, and of course it wants 8. And then we have a carbon radical, specifically a methyl radical. And if you look closely, that carbon has only 7 electrons surrounding it, 2 from each of the 3 bonds to hydrogen, and then that single electron. So it's one short of an octet. Now, not all radicals are equally unstable. Some of them can be more stable based on a variety of different structural features. One thing that really changes the stability of a radical is the size of the atom that is deficient in that electron. The bigger the atom is, the more stable the radical will be. So if you think of the halogens, we can order the halogens in terms of their size, fluorine being the smallest, and then chlorine bigger, bromine even bigger, and then iodine very large. So here I have the 4 radicals from those halogens. Fluorine, being the smallest of the halogens, is going to be the least stable halogen radical. Iodine is a very, very large atom, so as the halogen radicals go, it's going to be the most stable of the radicals. Several organic reactions involve the formation of carbon radicals, and there's a stability trend with carbon radicals as well. With carbon radicals, the stability is really linked mostly to the degree of substitution on the carbon that actually has the electron deficiency. The more highly substituted the carbon radical is, the more stable it is. So that would mean that a methyl radical, which has essentially no substituents attached to that carbon, is going to be the least stable. Then primary is a little more stable than secondary, and then a tertiary radical would be the most stable. So here the letter R is representing any alkyl group. It's actually a really common way of abbreviating an alkyl group. So a useful reaction that involves radicals is the radical halogenation. Radical halogenation is a substitution reaction that replaces a hydrogen with a halogen. It's a useful reaction because it can introduce functionality where no functionality originally existed. Specifically, it introduces a halogen substituent onto something like an alkane. The reaction requires a dihalide like F2 or Cl2 or Br2. The alkane or other reactant is treated with the dihalide in the presence of either heat or light. If you've never seen these symbols before, the capital delta is a frequently used symbol for heat, and then this expression here, H nu, it actually comes from Planck's equation, but it's a really common abbreviation for light energy. The reaction proceeds to give an alkyl halide and a molecule of a hydrogen halide as a byproduct. Now, this reaction has a major problem, because the product itself is reactive under the actual conditions. Think about it. The reaction proceeds to replace a hydrogen on carbon with a halogen. And the product itself also has hydrogens bonded to carbon. And that means that even a simple molecule like methane can react multiple times to give multi-halogenated products. So here we have methane reacting with Cl2 in a radical halogenation. The product from monohalogenation has CH bonds, and that means that that product can react with more of the Cl2 to create a dihalogenated product, which also has CH bonds, which can react further to give a trihalogenated product, and then ultimately replacing that last hydrogen to create a tetrahalogenated product. So this reaction is not terribly useful synthetically. If you were a synthetic chemist and you were tasked with making a certain drug molecule and you needed to use a radical halogenation as part of that process, you might end up making a whole bunch of different products, most of which you don't actually want. But while this reaction is not terribly useful synthetically, it is really useful industrially. Even with something like methane reacting in this halogenation, it makes 4 different products. And that's okay if you can sell that mixture, or if the individual components of that mixture are useful and you can isolate them from one another, then you can simply purify them and sell them individually. In the case of methane reacting with Cl2, the 4 possible products here are all very useful industrially. The monohalogenated product is a useful alkylating agent, and the other 3 products are actually very, very common organic solvents. So if you had a large-scale reactor, charged it with methane and Cl2, and you made this product mixture, You could exploit their differences in boiling points and simply separate them using a distillation. So, how exactly does the radical halogenation work? It actually proceeds through a chain reaction. And what we're going to look at here is really our first step into looking at reaction mechanisms. A reaction mechanism explains exactly how a reaction proceeds, how the bonds are broken, and how the various bonds are formed. So, the radical halogenation is initiated by cleavage of the dihalide with either heat or light. This results in the formation of two halogen radicals. One of those halogen radicals can then react with a molecule of the organic substrate. Here I have methane. That chlorine radical will bump into one of the hydrogens on that molecule and abstract that hydrogen, literally breaking the CH bond to form a ClH bond. And along the way, it's going to form a carbon radical. That carbon radical can then react with another molecule of the dihalide, breaking the Cl-Cl bond and forming a carbon chlorine bond. This results in the formation of a new chlorine radical. These last two steps constitute a chain reaction. The chlorine radical in this last step can go back and react with an alkane in the previous step, which generates the carbon radical that's required for the last step. These last two steps will continue until the supply of one of the reactant molecules is depleted. So the radical halogenation on a simple molecule like methane is pretty straightforward. What happens when you start reacting more complicated molecules? In methane, all of the hydrogens are the same. You can't tell one from the other due to the symmetry in the molecule. What happens when you have a molecule with different kinds of hydrogen? Here we have 2-methylbutane. And if you look at the structure of 2-methylbutane, you can see that it actually has four different kinds of hydrogen. We have these six identical blue hydrogens on these blue methyl groups. We have a unique red hydrogen on the red CH. We have the two green hydrogens. And then finally, we have the three identical methyl hydrogens on that black CH3. Replacement of any hydrogen from any one of those sets will result in four different possible products. These are actually constitutional isomers, and in this context, they're often referred to as regioisomers. If a reaction can form multiple regioisomers, but it prefers some over others, it's said to be regioselective. Now, it turns out that radical chlorination is not regioselective, and you can see that with this example. Reacting 2-methylbutane with radical chlorination conditions results in four possible products roughly evenly distributed, right? We get 28% of this product, 23% here, 35% here, and 14% here. It's not really very selective at all. However, radical bromination is regioselective. Radical bromination proceeds to replace the hydrogen on the most substituted carbon available. So here I have 2-methylbutane represented as a skeletal structure, and you can see that the hydrogen on this tertiary carbon, that's the most highly substituted carbon with a hydrogen on it, and that's the hydrogen that's replaced. And it makes one major product in this case. Now, the reasons for this regioselectivity are a little beyond the scope of a course like this, but it has a lot to do with the stability of the various carbon radicals that can be formed. If you think about it, removal of one of those blue methyl hydrogens would result in the formation of a primary radical. Removal of the red hydrogen would result in a tertiary radical. Removal of one of the green hydrogens would result in a secondary radical, and removal of one of the black hydrogens again would form a primary radical. And we know that radical stability is tied to the degree of substitution. A more highly substituted radical is a more stable radical. And that's why we end up with bromination replacing the hydrogen on the most substituted carbon, because it actually forms the most stable possible radical. And remember what we said about the size of an atom and its radical. The bigger the atom, the more stable the radical. Well, a bromine radical is bigger and therefore more stable than a chlorine radical. And that's why there's this difference between radical chlorination and radical bromination. The bromine radical is more stable, and so it tends to be more selective about which hydrogen it abstracts. The chlorine radical is so reactive that any hydrogen it bumps into, it just pulls it off immediately. And that's why you wind up with this complex product mixture in chlorination, but a high degree of regioselectivity in the radical bromination.